Good afternoon. It's my pleasure this time to introduce Martin Bichler, who kindly accepted our invitation to come for DTU Summer School. A bit about Martin. Martin is head of Computer Science Department at Technical University of Munich. Also, Martin is heading a research group on decision sciences and systems. Martin is also affiliated with TUM School of Management and also a core member for Munich Data Science Institute. Martin had a long list of visiting stays, awards, and grants. Just a couple of them to mention. Martin granted a DFG project from German National Science Foundation on economic sciences. Also recently secured ERC Advanced Grant on learning games. And I think you will talk a bit about that maybe today. Martin's area is at the intersection of computer science. He knows himself as a computer scientist, you said. Also at the intersection with computational economics, operations research, and also some applications with power systems. So we were talking that you've been working a lot on pricing electricity markets. For example, under non-convexities, he has been working on European day-ahead market euphemia algorithm, and also you've been a member of ENSOI's working group on revising bidding zones in Europe. So Martin, the stage is yours, and again, thanks for coming.
Thank you so much, Jalal, for this very nice introduction and for inviting me here. It has been a pleasure. You're an amazing host, I can say. It wasn't difficult for me to decide to come here. This seems to be an amazing audience. And we exchanged some ideas on what I'm going to present. Part of it, the initial ideas were learning in games. Then I realized the focus is really very much on electricity market design as well. And there have been, over the years, a couple of talks. And I thought I can contribute maybe a little bit on that end, right? So the title is a little different to the one that you find in your program. It says Theoretical Foundations of Non-convex Markets, which is what nicely describes electricity markets. And I want to talk really about some of the fundamentals from an econ perspective, but always reach out to the very specific application that you're all interested in, right? So the key question that I want to address in the time that I was given is, understand economic foundations of market design relevant to electricity markets. So if you go back to the early 90s, mid-90s, when many of the power exchanges were introduced, the argument was all along, well, that's the way to do it because it's more efficient, right? And people stop there often, and there is a vague memory that people might have on Adam Smith saying, well, a market will lead to an efficient outcome, more or less, or the invisible hand, how he called it back then, which was kind of made a bit more precise by then. And I think that the question that I want to address today is, when can we expect markets to indeed find an efficient outcome? And I want to be more precise what I mean with efficient, allocative efficiency. And when is it maybe too much to ask for, right? So I was asking Jalal, what are prerequisites that I can assume here, because I understand it's a very broad audience. So I tried to keep it on a level such that if you had an introductory class into linear and integer programming and know a little bit about complexity theory, then you should all be good. And if there are any questions, just reach out, ask, right? Feel free to interrupt any time. Right? So what I want to start out with, and this is what usually was often referenced back then when it came to using markets to do resource allocation and create these spot markets, was the welfare theorems, right? So they are very well known. What you see on the left-hand side is this partial equilibrium that goes back even to Marshall, a textbook from the 1900s. So this is something everyone has seen. But the welfare theorems, just to remind you, this is work that goes back to Arrow, Nobel Prize laureate, as well as Debreu and McKenzie in the 50s. And what they showed in their work on a fairly abstract economy is that a competitive equilibrium where supply equals demand is Pareto efficient. And we will make all of this way more precise as we go. And every Pareto efficient allocation can be supported as a competitive equilibrium, right? And you will see different versions of this as we go through it and make these models a bit more tangible. The models back then, I'm not going to revisit them because they made a lot of assumptions, right? So first, all the goods are perfectly divisible. And the preferences are convex. So things that you see on a European day-ahead market where you have these block bids where you can submit bids on multiple megawatt hours in a day or so. This would not be convex preferences, and we will discuss this a bit more. Bidders are assumed to be price takers, so they are not trying to manipulate, they are not bidding strategically, they see a price and they make the best decision, which you can also challenge, of course, and at least some of the results, like whether a competitive equilibrium price vector exists, are pure existence results, right? So these are fixed point theorems that says, well, such a price vector has to exist. So essentially what they analyzed as compared to the partial equilibrium model that you see to the left is a competitive equilibrium in a market where you have many, many goods, okay? And even back then in the 60s, people challenged that. So Georgescu Rögen would be one of the names that comes to mind, was a Romanian economist who said, well, you know, these assumptions are not real world, right? So what do we learn from this? And there's a lot of credit that was given for these results, but is it really helpful to understand, right? So essentially, the key questions that we want to discuss today is we want to relax some of these assumptions, arguably very strong assumptions. So first, what happens if you have indivisible goods? And more importantly, what happens when we deviate to non-convex preferences? And I hope I can convince you that this is what essentially describes electricity markets. So the preferences and ultimately the resulting allocation problems and clearing problems are non-convex problems. And then pricing becomes a bit more of a challenge, and this is what much of the electricity market literature is all about, right? And I decided to structure my talk after 3 subjects reminiscent of old Western movies: the good, the bad, and the ugly, right? So the good is, there I want to talk about what we nowadays call convex markets. So you might remember from optimization, Rockefeller's statement, the real watershed in optimization is not linear or nonlinear, it's convex or non-convex, right? And you can actually transfer this to market design, right? So if you have convexity, you find really nice solutions with nice, in particular, economic properties, right? So, and we want to start out with the simplest model that you can think of, which is by now 55 years old. It's the so-called assignment model. So it's a model where there are multiple objects, there are multiple market participants, but they're all interested in winning at most one of the items, right? So you might say, well, there are maybe not that many of those markets, but it's one of these really nice models where you can check all the boxes. You get a lot of really nice design desiderata satisfied, right? And this is kind of your wish list. And then we will relax some of these assumptions. So we go to multi-unit demand, right? So often you are not interested in not only buying 1 megawatt hour, but maybe more, right? So and what happens then? And how can we find prices? How can we compute the clearing? And I'll give you a couple of properties when we can actually find competitive equilibrium and competitive equilibrium prices. And when I say competitive equilibrium, this would be a price vector. If you look at it and you look at your allocation, you would say, this is exactly what I want, and I don't want anything else. And if all of the participants have the same reaction on this price vector, then this is going to be a competitive equilibrium in the sense that nobody wants to deviate, right? So, and we will have a more precise definition later on. Then in the second part, the bad, we talk about non-convexities because that's essentially what we see on these electricity markets. It's, by the way, not a property that is so specific for electricity markets. You could argue that many markets nowadays for transportation, for spectrum, they are all non-convex markets. So they share the same types of difficulties, right? And we talk a little bit about the types of prices that you might need there. So you might not get away with simple linear prices, meaning one price for 1 hour of the day, say. And we talk a little bit about approximating this idealized notion of competitive equilibrium that we might not always get. Okay. And then the last part, I called it the ugly. This is when budget constraints hit. So there are actually a few papers that even in electricity markets say, well, you know, we have lots of volatility. I would love to submit a bid that says, well, this is what I need over the day, but if prices due to some energy crisis go crazy, I'm not going to pay more than X, right? So you have a budget constraint on top, right? This is a requirement that you find on many markets, and I hope I can convince you then this is becoming a really, really hard market design problem. And when I talk about hardness, what I really mean is computational hardness, right? So this is going to be what we go through until 4:15. And again, if you have any questions throughout, just raise your hands. So let me start out with this assignment market. This is, in economics, a very traditional model, and it goes back to Shapley and Shubik, two of the great minds in economic theory. Was published in 1971, and let me briefly describe what it is. So first of all, what do we assume now on the participants? They just want to maximize profit, right? And I'm going to call this a quasi-linear utility function. Quasi-linearity means I have some function that determines the value for the goods that I'm interested in, and that can be arbitrarily nonlinear minus price. Right? And so it's really value minus price. That's what I want to maximize. And I'm interested as a bidder in this market in one out of multiple objects. So this is what you can see on the right-hand side here. K is going to be the items, I is the bidders, and then this V, I, J, this is essentially the values that a bidder has for each of the items, right? And that's it. And in order to have M equal N, we might fill up, so if there is more bidders than items, we might fill this up with dummy items, right? So if we have a problem like that, this is, well, you probably know what that is, right? So this is the standard bipartite matching. So that's at least in computer science how we call it, or the assignment problem, right? So one bidder wants exactly one, at most one of these items, right? And this is, if you had any linear programming class, one of your initial exercises that you go through, because it's so nice and simple. So there is a very well-known algorithm, the Hungarian algorithm, to solve this problem optimally, right? And that's what we draw on. So it's in polynomial time, as you can see here, you can maximize welfare. And I'm going to show you in a bit how the model looks like. So that's nice. We can solve the problem in poly time. In energy markets these days, that's not what we can do, right? We get Walrasian competitive equilibrium prices. I already told you a little bit what I mean by competitive equilibrium prices. Walrasian here, I'm going to use it in the sense that for each item I have one price only. And I will tell you later that we might not always get away with this, right? So we need a more complex price function. What is super nice in this market is it is group strategy proof. Strategy proofness is kind of another word for dominant strategy incentive compatible. So there is really no reason to lie on this market or to bid strategically. So if you look at this market, you have a simple dominant strategy, you reveal your valuations truthfully, and that's it. So group strategy proofness is something on top. So even if there's a group of you as bidders that flocks together and says, well, how can we somehow, if we know everything, manipulate this market in our favor, it's not going to be possible at the prices. So this is an extremely strong property that you rarely have, right? And last but not least, there is a very simple ascending implementation that I'm going to show you in a bit, which is essentially an algorithm that raises prices in a systematic manner such that you end up in a solution that is, first of all, maximizes welfare, this objective function, and the prices that you get are the lowest competitive equilibrium prices that you get, which at the same time is the reason for this algorithm to be strategy proof, right? So this is essentially the wish list that you ideally would like to have for every market, right? Nobody needs to manipulate. You get the optimal solution with a very simple algorithm, ascending algorithm. So this is kind of neat. And the whole theory really follows from linear programming and LP duality. And we're going to go through it briefly. There is one assumption that I didn't specify in detail, which is, I said, we maximize welfare. And economists usually are very careful when it comes to the word welfare. And one of the insights, if you look at in economic theory textbooks, for example, is that if we have this quasi-linear utility function, if I maximize aggregate surplus, so I pick an allocation such that the total of all of your utilities is maximized, then this is going to be a strongly Pareto efficient solution. Meaning there is no way how I can find a better allocation where I can at least make one person better off. Okay? If we pull this assumption, then the question is what is welfare? So what is behind this quasi-linear utility function that I was explaining, so value minus price, is that the marginal utility for money is the same, right, among all of us. Right? Which you could challenge, right? So if there is Elon Musk in the room and me, the marginal value for utility might be different, right? So, and that goes back to European social choice and so on and so forth. Let me not get lost here at this point. I just want to highlight this seemingly innocent assumption of this quasi-linear utility is maybe not as innocent, and we will get back to that towards the end of the talk. Okay, so but for now we assume we all just want to maximize profit, value minus price. So this is essentially the model that you could look at, and this is your kind of 101 in linear programming kind of. So what do you see here? The objective is you maximize aggregate value. So we have what you saw on the last slide. Each bidder has a value for each item k, and then xik is a decision variable. It's binary here. And then the set of constraints is also fairly straightforward. The first one says, for each item, you need one winner or one assignment, and the second is for each bidder, you need one item, right? So that's what you want to have satisfied. And if you take a look at the dual variables here, they have a neat interpretation. So the duals can be interpreted really as prices, a price for the item k here. And pi I would be the dual variable of the second set of constraints. This can be interpreted as the profits. And this is becoming a bit more obvious if you look at the dual here. So this is kind of the objective function for your dual. You minimize the sum of the payoffs and the sum of the prices, so the dual variables here. And we have one dual constraint. And to make it even more obvious, what I'm going to write down now are the dual complementary slackness constraints. So this is how it looks like. So either I win something, then this dual constraint is tight. Right? If I win an item, then this dual constraint is tight. What does this mean? Well, then I maximize my payoff. So, and my payoff is then value minus price if you move it up over to the other side, right? And that's exactly what a competitive equilibrium is, right? And so complementary slackness in this model is exactly the competitive equilibrium condition. So at this price vector, once I find it, every winner maximizes his payoff, and nobody would want to deviate, right? And this is kind of neat, right? So now you have a very tangible model of how such a market would look like. Okay? Good. So I was also promising you there is a very simple algorithm to solve this. And I'm going to show you in a little example how prices are developed here. And I'm going to give you the more general recipe thereafter. But for now, what you see here, these are the bidders, these are the items, A, B, and C, and the numbers here are really the values that each bidder puts on an item, right? Very simple. So the stars here mean this is really the optimal assignment. So this is the assignment that maximizes aggregate welfare, okay? And what I'm going to show you is essentially if we go through a couple of steps where we iteratively just raise prices, very much like in an English auction, and it is indeed a generalization of an English clock auction, then we will end up at this assignment, right? So what am I doing here? The first bidder, the most valuable item to him would be B, the second B as well, and the third bidder B as well. So what I'm doing, okay, I raise the price to 1. Right? Always 1 nudge. Then I deduct this 1 from the value, and this is the remaining payoff here. And again, I can look at the boxed entries. These are the items that maximize payoff. And I always increase the price at the set of minimally over-demanded items. Right? In this case, it's B again. Right, then next I have now 2 items that are over demanded, so I'm going to raise the price on both of them, so you have 1 and 3. Round 3 the same thing, round 4, round 5, and I eventually end up here, right? So what do I get? Well, if I end up here with all the boxed entries, I can draw on Hall's theorem and saying, well, now I can find a perfect matching. A perfect matching in the sense that every bidder gets 1 item. Okay, and it's obviously has to be, I assign C to bidder 1, A to bidder 2, and B to bidder 3. And that's neat, kind of, right? So this is exactly what we wanted to get by an example. So I've, again, think of it as a generalization of the English auction, where in a systematic way I raised prices, and it doesn't look too complicated. It turns out that this is indeed a version of the Hungarian algorithm. And the Hungarian algorithm itself, as many of you might know, is nothing else but a primal dual algorithm. A primal dual algorithm is kind of a general recipe how we solve linear programs. Right? And that's actually what's going on here. So we start out with the original primal that I've shown you a few slides before. We take the dual, then we take a look at the restricted primal out of this. And if we can solve this, then with a particular objective function, we are done. So this is where we end up here. If not, then we look at the restricted dual. The restricted dual tells us where to raise the prices, and we go back. And kind of to give you a bit of an intuition, do we have chalk here? Oh, okay. So we had 3 bidders, 3 items. This is K, this is I, right? And at the beginning, this is kind of fully connected. And when I talk about this restricted primal, essentially we take a look at a subset. So at the beginning, this was item B, and all the bidders were interested in item B. I just zoom in on this restricted bipartite matching, and I see, all right, so there is over demand here, this is where I'm going to raise prices, and so on and so forth, right? So it's a very simple recipe that everyone who took an introduction to linear programming can solve, right? So what is actually more is that this type of model allows for a strategy-proof outcome, right? So the way how this algorithm works, it stops at prices that are the lowest prices in the core. I'm going to explain the core in a bit, but at the lowest possible prices, let me put it that way. And these prices have a particular property. They coincide with the results of the Vickrey-Clark growth mechanism. I'm not going to talk a lot about incentive compatibility because we can't get it anyway for the markets that we look at. But it's strategy proof really means, again, if I follow this this algorithm and I get these prices in each round, my best strategy, and it's to be precise, is ex post incentive compatible. My best strategy is just to reveal my preferences truthfully. And bear in mind, so this algorithm, I never reveal what my value is. So these are only demand queries. I just say, well, at these prices, these would be the items that I'm interested in. Right? So this is really what a market does, right? And the question is just how do you get to these prices? So and if we follow that recipe and that simple algorithm, then we end up at prices that where you can show it corresponds with the VCG prices. Why is that important? Well, in this quasi-linear model that we talk about, there are some more fundamental results that show that VCG is unique. So it's the unique in this quasi-linear model, the unique incentive compatible mechanism, right? So, and if we end up there, we also know, we just implemented the Bichler-Groves mechanism, right? There would be a lot to say about incentive compatibility and strategy proofness. I'm going to skip most of this, and if there are any questions, we can talk about it in the break. So the key paper here is Demange, Gale, and Sotomayor from the mid-80s. And they allude to the Hungarian algorithm with a single line, and the rest of the paper is just to prove that actually, indeed, when you follow these steps of the algorithm, you end up in the Bichler-Groves result, right? So, so far so good. So we have one particular market where we really get your usual wish list as from an econ point of view. So this is kind of a proof that Adam Smith was right. So you get everything you want, right? You have a very simple ascending algorithm that ends up in a welfare maximizing solution. And I was telling you at the beginning, if we maximize welfare, so the sum of the values of everyone, then this is going to be strongly Pareto efficient. This is what economists care about. So the question now is, well, can we push this any further, right? And you will agree, limiting bidders to be interested in at most one item, this is a bit restricted. So let's take a look at an extension of this where people are interested in a bundle, right? So how would you read this? This is just the objective function here is your value. Now x is a particular vector that tells you how much do you want from each item, from each commodity. Vi is the value for this particular bundle, and zi of x of this particular vector is a binary variable. So do you win that bundle or don't you? Okay. Then we want to enforce that you can win at most one of these bundles, right? You just enumerate your preferences for all these possible bundles, and then supply equals demand type of constraints. So if I sum over all the demands, they must not exceed the supply here. Sk is how much supply is there for a particular commodity. Okay. And of course, we can take the dual, right? And it looks actually fairly similar. If you take a look at this, we have this objective. So we minimize the sum of payments and the sum of quantity times price. So these are the dual variables, look very similar to what we had before. And we have a dual constraint that also looks pretty much the same, right? So pi I, if I move this over to the other side, the value minus the price that I pay for this particular bundle, then this is going to be my payoff. So, and if the dual variable x is, or z here is positive, then this would be tight. So this means everybody would indeed, as we had before, maximize his payoff at this price vector. All good, right? So what's going to be the problem here? So bear in mind that we have binary variables here. We relaxed it, right? So before that was not a big issue. Why was that not such a big issue? Well, the assignment problem has a particular property. It's totally unimodular, so we know whatever solution we pick is going to be integral as long as the right-hand sides are integral, right? So easy. That's not given here, not necessarily. So it's not unimodular. So this constraint matrix is not, right? And that's why this breaks. So the sufficient condition at least doesn't hold. Okay, so here is a little example to make that as clear as can be. So we have, so these are the x's, so these are the particular vectors that you might be interested in. So either you want nothing, or you only want the A, you only want B, you only want C, or A and B, and so on and so forth. And these are the values that you might be interested in, right? And if I'm solving the linear program that I was just showing you, then I get a fractional solution. Right? No surprise. There is no guarantee that the relaxation would end up in an integral solution for these types of linear programs. So, for example, I would assign half of B to 1, half of AC, the package, to 1, half of C to 2, and half of A and B to 2 as well. And that's not what we want. We actually want integrality, right? The objective function value of the relaxed winner determination problem is going to be 4.5. And if I enforce this integrality constraint, the objective function is going to be 4. So what can I expect from the prices? The prices meaning the dual variables of the relaxed winner determination problem, they are too high, right? So they might be inflated. And if this demand here is very lumpy, then the differences and the MIP gap can be huge, right? So in general, there are no guarantees yet. So let me get to the first, a bit more precise definition of a Walrasian competitive equilibrium. So it's a price vector P star and a feasible allocation x1 to xn. Feasible, I mean that one that satisfies the integrality constraints. And they form a competitive equilibrium if supply equals demand, so S is equal to the sum of the xi vectors, and this is something I have to explain, X is element of the demand set. So the demand set is, I give you a vector of prices, you look at the prices and say, well, this is the bundle that would maximize, or these are the bundles that would maximize my payoff. That's your demand set, or demand correspondence. And that's this function. Right? So again, if a competitive equilibrium is if everybody maximizes his payoff at those prices and supply equals demand. Okay. And there is a nice paper from end of the 90s that for anyone with an OR optimization background is quite obvious in a way. A Walrasian competitive equilibrium exists if and only if the relaxed winner determination problem has an optimal integral solution. So we've seen that was the case for the assignment problem, right, where you have this one-on-one, but it's not generally satisfied otherwise, right? Okay. So a reasonable question to ask now would be, all right, maybe there are some additional properties. We talked about total unimodularity, sometimes holds, right, but not always. But can we expect such winner determination problems to yield an integral solution? Because if we can, or if we know that, well, then we can just draw on the dual variables and we have prices. Okay. So there is a whole field that some of you might be familiar with in math, which is discrete convexity, right? So a function f that maps to the real numbers here is called integrally convex if the local convex extension of f is convex, or integrally concave just if it's the negative of this function. So there is one condition that was interestingly historically discovered in economics, and it's very prominent there. So if you ask a random economist, he would know what a gross substitute is. Gross substitutes is one of these conditions that people really care a lot about because you get a lot of nice economic results. And this was first published in a paper by Kelso and Crawford in '82. And in parallel, in math, people came up with similar notions and later on realized, oh, we're actually talking about the same thing here, right? So let me briefly explain or give you one definition that you find in econ textbooks about what a gross substitutes mean. An agent is said to have a gross substitutes value if whenever the price of some items increases and the prices of other items remain constant, the agent's demand for the items whose prices remain constant weakly increases. Right? That's a bit of a mouthful, I have to admit, right? And it's a bit of an informal discussion. And what makes it a little hard is it's not on the properties of the value function in itself. So it is a definition that requires to look at prices, at kind of the dual variables, right? So there's a whole literature on growth substitutes, right? There is a nice paper by Lehme from Google from 2017 that summarizes all the different notions of growth substitutes. M-natural concavity is the term that people in math use for it, and it's actually equivalent. We came up with a definition that goes via Minkowski differences. So there are different ways to describe the same beast. It's not super intuitive. So I think that's probably the most intuitive definition that I could find. So if you go into some market and ask yourself, well, are our bidders most likely limited to growth substitutes valuations? It's actually not hard to decide, or not difficult. And there is an extension of this to strong substitutes. This is when we look at multi-item, multi-unit settings. So growth substitutes is the definition that we use if we have one unit of each item. And if we have a market where we have varieties, where we have different commodities, but multiple units of each, then you would look at the strong substitutes. But it's kind of the same principle, right? And again, there's a huge literature in economics that looks at this very specific condition, which is a sufficient condition for integrality of the resulting linear program. Right? So far so good. So now we have one sufficient condition at least, and suppose it's halfway accepted. I haven't told you yet how to get to prices. Right? So let's assume you all have growth substitutes preferences. I have a market like this, and now I want to run a market. So I collect all your bids, and I impose on you that you're truthful. You all look truthful. So suppose I get your true values, right? So now I want to give you this competitive equilibrium price vector. How would I do that? Just computationally, right? And interestingly, this literature is fairly young. The first paper that I know of is by Larry Ausubel from Maryland, which is an unpublished paper in 2005. But there is a bit of literature thereafter, Morota in math, Elizabeth Baldwin, Paul Klemperer, and so on and so forth. What they all use is a Lyapunov function. Some of you might be familiar with Lyapunov function from a very different field. It's control, it's dynamical systems. That's when you want to prove asymptotic stability of a dynamical system, for example. That's when you draw on. So here it's a little odd in a way, so because there's a very specific definition that they all use, and it's this one. So it's a function of price, of a price vector, and this is the so-called indirect utility function that gives you for each price what the demand is going to be in this market, plus the dot product of prices times the supply that is available. And this is a bit weird because it somehow falls from heaven, right? So what is the rationale, the intuition behind this specific function? So we looked at this, and one of the things that, if you take a closer look, is this is actually very related, and you can show it's equivalent to your dual restricted winner determination problem that I've been showing you before, right? So let me just go back quickly. So here, this is the objective function of your dual here that we are thinking about, right? And what you can do is now you can take this and substitute this into your objective function. Then it becomes one function. And if you do this, it becomes, so this is what you get. So this is kind of your indirect utility, the maximum allocation that, value minus price again, plus this SK times PK. So essentially this Lyapunov function that you find so often in the literature, this is essentially your dual restricted winner determination problem that I've been showing you before, right? And if you have this, then you can either use a primal dual algorithm again. You can run a subgradient algorithm on a function like this, and it would always get you an optimal price, or an optimal price in the sense of a competitive equilibrium price. Right? So if this is too much formulas. I thought I give you a very simple example to make this as tangible as possible. So here, how to read this? This is the aggregate value function, and as you see, it's concave. So great, if we have concavity of the aggregate value function, that's what we want to have. So how to read this? So the first guy wants one item or one unit of one commodity, and he's willing to pay up to 5 euros. The second guy, 2 euros. The third guy, again, 2 euros, and so on and so forth. So this gives this concave shape. You can derive from this indirect utility function. So now bear in mind, this is the quantity. This is now price here. And you see it's kind of convex. And now if I add this additional term, S times P, then I get this concave function, which has a minimizer at 2. So 2 is going to be the competitive equilibrium price. So I get this concave Lyapunov function, and I take a subgradient algorithm that finds me the minimum of this function. And that's going to be the competitive equilibrium price. Okay? So that's kind of neat, right? So I have a very effective, fast algorithm. I do essentially discrete convex optimization, and I'm done. Okay? Good. So where are we? I've shown you a very simple recipe to find a competitive equilibrium price on a market. And this recipe is model the allocation problem as an optimization problem. If the problem is convex, good for you, then the duals can serve as competitive equilibrium prices. We have very fast iterative algorithms, so there's a whole literature on discrete convex optimization. Subgradient would be one of your choices, or these primal dual algorithms. What is nice, let me drive home that point. If you look at this algorithm, so this algorithm, primal dual algorithm, really is a model for a distributed economy. Why is that? So if you compare that to the simplex algorithm that all of you know, the simplex algorithm in each iteration, it needs access to the true valuations. If you saw the example that I went through, the bidders never revealed their true valuations. So they were given a price, the dual prices, and then they said, okay, with these prices, this is the bundle that I would be interested in. And that's essentially how an auction looks like, right? What I'm trying to tell you is we can use algorithms that we have developed in math and computer science as an economic model. Due to the revelation principle and some other history, such models of dynamic markets are actually fairly rare and a fairly recent phenomenon, right? Good. What are the problems with all of this? First, I told you we get incentive compatibility and even group strategy proofness in this assignment market, where we have these really restricted preferences. You want at most one item, right? Beyond that, no hope with these types of market mechanisms. So the competitive equilibrium price vector and the VCG prices are just different things in general, right? So there is, if you had all the information, there could be ways to manipulate this market, right? So if you're not just a price taker, but you strategically submit prices such that you want to lower your own price, then there could be possibilities. We can't rule that out. The difficulty is also, do you know a priori if the substitutes condition holds? I was reading it off. Again, it's not a totally intuitive definition. And how would you know before you run a market whether this condition is satisfied? And more of it, in many cases, we actually know that it's violated, right? And this is when we talk about non-convex markets. So Dick O'Neill, I think, used this term quite a bit. He was one of the people who really influenced market design in the States quite a bit, and I think worldwide. And maybe last point, if you think about the set of all possible valuations that people can have, substitutes is a really, really restrictive condition. And it's interesting if you look at the economics literature, how much attention is given to this one condition, probably because you get nice positive results. If you have, if you go a little broader, that theory would not hold anymore. Okay? Good. Are we doing in time? Yeah, let's crack on a little bit and let's go to the bed. Are there any questions so far? Right? So again, this is very much like in optimization. If you have convexity, in this case convexity of the aggregate welfare function, then nice things happen. The gross substitutes condition, let me also point that out, it's a condition on the individual preferences. But it's such that if all of the participants in the market satisfy this condition, then we know that also the aggregate value function that I was showing you is going to be concave. Okay. Good. Let's get to the bad part. Bad in the sense that, okay, convexity is not given, still we need prices. Many allocation problems, I mean, if you look at the literature of OR, I mean, most of it is about non-convex optimization problems, you could argue, right? And this is what kept our profession busy for, I don't know, 50 years now or so, right? And electricity markets are one nice example, right? Talk about vehicle routing, talk about spectrum allocation, whatnot, right? So many of the real-world allocation problems that we find are just non-convex optimization problems, or can be modeled as such. So we are mainly interested today in day-ahead electricity markets, and I will give you a couple of formulations a little later to convince you, okay, this is a non-convex problem, right? So it's in particular the complexity of the constraints. So for example, these block bits that you find. So I'm interested in electricity from 7 o'clock in the morning to midday, kind of, right? And that amount. That makes it not convex, essentially. And one way to model these things is mixed integer linear programs, as you all know. Volume discounts more broadly. So you find this in procurement, you find this in transportation tenders, and everywhere. The good news is in operations research and applied math, we've become really good in solving these problems, right? So this is actually, I should have quoted this explicitly. This goes back to Bob Bixby, who some of you might know. He's the original inventor behind Cplex and Gorobi, some of the most effective solvers that we have today for mixed integer linear programs. Right? And he did the math. We had him over in Munich a couple of years ago, where he gave a keynote, and he showed very convincingly on particular problems that the performance increase is really breathtaking. So it's like 1 million times performance increase, and I'm only talking about the algorithmic side. So we are so much better in solving larger and larger mixed integer programming problems, right? So that's good. That's why we can solve electricity markets since about 25 years, right? But you also all know IP duality is a beast, right? So we can't draw on duality anymore, which probably became clear already in the last couple of slides, right? So that's a bit of a bummer. So what I want to focus on in the next section is really, well, we need something like prices. On electricity markets only work if we have prices. We can't use the standard recipe, just take the dual variables. What can we do? And is there some theory that guides us? Okay. So let's first jump back to electricity markets and talk a little bit about what do I mean with non-convex and where does all of this come from. So this is something that I suppose most of you probably have seen, right? Can you maybe raise hands briefly? The unit commitment and economic dispatch problem. Okay, very good. So. So this is your textbook model. Let's just briefly go through it. We have the objective is has this unit commitment variable. So whether a particular generator is turned on or off, it's binary, and it comes with some startup or fixed costs, right? And then we have marginal costs for the quantity that you're going to produce, and then we have for each node, we have a particular quantity that we want to produce that needs to be produced on that node. It must not exceed, so if we produce, then X1 is turned on, and it must not exceed the capacity of the generator, and of course, what is produced must not be negative, and so on and so forth. So fairly simple to read, and it's obviously this binary condition that makes it non-convex. And this corresponds nicely to these US-American bit languages that they use there, where you can quote a cost for startup of a generator, for no load, and for variable costs. And that really feeds into the objective here, right? So this is already where you have issues with with just looking at the duals. And the pricing rules that are being used are very cognizant of this, but let me not get ahead of myself. We're going to cover some of those as we go. Okay, so this is the US side of things, where of course the real world is always a bit richer and more complex, but this is kind of the fundamental model people look at. Let's talk a little bit about Europe, because the market design in Europe, as many of you might know, is different. So one of the big achievements in Europe is really that we managed to couple all of these markets. In the US, you might know, there are a couple of ISOs. There is CAISO in California, there is ERCOT in Texas, and so on and so forth. But they are kind of really independent, and they cover a particular range. There is an obvious insight from econ. If you have larger and larger markets, you know, that aids efficiency, and that's the route we took in Europe. And since I think 2014, there was more and more coupling, and all the green countries here that you see are now in the SDAC, the single day ahead coupling. So this is these numbers might be a little bit outdated. I just took them from the NSOE website, but roughly to give you an idea, it's most of the EU consumption. It's like 200 million euros average daily value of matched trades. I think these numbers might be higher now, but this is roughly 70 billion a year, right? So it's a huge, huge electronic market. We're talking about around about 16,000 generators, 25,000 nodes, and 22,000 lines. So this is huge, right? And it's solved via a mixed integer program, right? Or not one, actually it's a whole series of mixed integer programs that are referred to as Euphemia. And we have a different bid language as compared to the United States. There is portfolio bidding, and people can either bid on individual market time units. So that would be, that for a long time was an hour, and they moved last year to 15 minutes. Which made, and we had a bit of a discussion on that, the resulting mixed integer programming problem way larger. So, and they are actually struggling. So they had to solve these problems indeed of that size in 17 minutes. And Jalal was just telling me, no, they are way beyond. So in many cases by now, due to the fact that you have many more products. And what is distinct is also not only, you can not only submit hourly bids or well, in this case, 15 minutes bids, so you can also submit these block bids. Again, always when I talk about block bids, what I mean is packages or bundles. So, you know, from 9 o'clock in the morning to 11 o'clock, things of that sort. And that ultimately makes it a combinatorial exchange. So this is probably the biggest combinatorial exchange worldwide, right? So things are a little different, and I'm gonna nail down what the differences are between Europe and the US in a bit. But let's talk about these combinatorial exchanges, and now I go back to our stylized simple examples. Okay, so we have A, B, and AB, right? So the package, and this could be market time units or some other commodities, doesn't matter. So I just wanted to come up with the simplest possible combinatorial exchange. We have two buyers, buyer 1 and buyer 2. These are their values for the individual items and for the package. And 7 maximizes welfare. So in a way, we suppose the seller has no value for the bundle. And if he can assign it to buyer 2, he gets 7. So 7 is the welfare generated, depending on how we set the prices. So that's maximal welfare. So what prices would clear the market? So consider everyone other than this bid is a loser, right? So the prices should be higher. And we are aiming for linear prices, meaning I want to have a price for A and for B only. Mm-hmm. Perfect. You looked at the slide? No. Very good. So fairly easy, right? So you have 2.5, 4.5, and then essentially this guy knows why he's losing, and everybody else understands why he's So why he's winning and everybody else understands why they are losing, right? So now I have a tougher nut to crack, right? So take a look at this example, and first we look at a setting where we have one seller who sells A, B, and C, right? One seller only, which is going to make a difference. And I didn't give you the values for individual items. They don't matter yet, but these are the preferences that we have here. So now I'm looking for a price for A, B, and C that clears the market. How could we set individual prices for these three items such that this guy, so the seller knows, or bidder 3 knows that why he's winning and why all the other, and everybody else knows why their bid is lost. It's difficult, right? So think about it. So we need a price for A and B together that is higher than 30, right? For B and C as well. And at the same time, the package of A, B, and C needs to be less or equal to 41, right? So that doesn't add up. So if you would just do it equally, 15 for each of the items, we are already at 45, right? So there are no linear prices, right? That's not possible here. So, and that's easy to see from these inequalities. So by the way, there is a typo here, so this should be the other way around. So we would need to have a price of larger than 45, and that's not given, right? So the only thing how you can deviate here, and that's what I want, the punchline of the slide is, we need a richer price function. We need nonlinear and personalized prices, and you can show that they always exist. So I just differentiate. I say, okay, buyer 1 gets a price of 30 plus something for A and B, and for B and C he gets a price of 10 plus something. But we all of a sudden lost the linearity, and that's going to matter quite a bit in electricity markets, right? So these prices don't exist. Now a tougher question. So I was telling you at the beginning. This is a setting where we have one seller. Suppose now I have a seller for A, a seller for B, and a seller for C. What's going on now?
You cannot set linear prices for each good. Then it's very difficult for them to agree on the price to be set, right? Because someone needs to make more money.
Right, so I already dropped linear prices. Let me be clearer. So even if you go for non-linear and personalized prices, how would you set them? So the challenge is here, suppose again, let's start with 15 for A and for B, right? Well, if I set the price here at 15, or let me start with the efficient bundle, right? So this is 13 point something. So obviously, the seller of A and B and the buyer 1 can deviate, right? They can get a better bargain if they say, all right, before A and B sell for 13 point something to buyer 3, I can get a much better price if I sell to buyer 1 for 14, say. Okay, so there is a coalition that can deviate. Suppose they do this and they determine a price of 14 or maybe even 15. What can happen? Well, then there is buyer 2 who is willing to pay 30 for B and C. The seller of C currently makes no money, right? So he could say, okay, I'm going to charge epsilon, so he's going to make some money, and I'm paying 15.5 to B, right? And then this coalition is better off, right? B and C and buyer 2. And the same thing for A and C, and so on and so forth. So the insight here is there is no core solutions. There is no stable solution where there is not some coalition that could deviate. I'm going to define the core a little later. But for now, what you should just remember is the core is the set of all competitive equilibrium prices that can exist. So there is no competitive equilibrium prices, even if it's nonlinear and personalized. So that means a market must not always have a competitive equilibrium under these assumptions, right? And that sounds like a contradiction to the welfare theorems that I was telling you at the beginning, but now we have more specific assumptions, and that's just not going to work. Okay, so these are the key insights. Competitive equilibrium prices, if I have these non-convex bundle preferences, think about block bits on the European exchange, they need to be nonlinear and personalized, and even then, I might run into situations where they just don't exist. I don't get a stable outcome where nobody would want to deviate. Okay? Good. So what we did so far is guessing, right? So we tried to guess prices that at least clear the market. That's maybe not what we want to do. So is there a more principled way to get to prices? And one way would be, let's go back to our math program and see if we can derive some useful information from that to set prices in a more principled way. So this is now a linear program for this exchange, right? So here I have buyers and sellers. So Z is going to be the packages that the sellers sell. S are the packages that buyers are interested in. I are the buyers, J are the sellers. What I want to do here in the objective is I want to maximize gains from trade. So which is also means I want to maximize welfare. So what the buyers put on the market, on the table, minus what the sellers are asking for, this difference I want to maximize, right? And that's essentially the objective function of electricity markets as well. Okay. This is just supply equals demand. So this is quantity here. Then we impose the same constraint that everyone in our model world can win at most one item. So they enumerate all packages and their values, and they can win at most one. And these are binary variables. Okay. Well, then we have a price for each item. We get a linear price out of this. These constraints are just the payoffs, again, very much like what we've seen before of the buyers and the sellers. So far, so good. What's the issue here again? Sorry? Binary variables, and these prices might be way off, right? So, because nobody tells us that this is going to be an integral solution. Most likely it's not. Okay? So, there is an interesting line of research in theory in math, which is extended formulations. Right? Extended formulations is essentially, I have some non-convex problem and I try to strengthen the formulation. I add additional cuts, for example. So can we do this here as well? And then we might have, like, maybe ideally we describe the convex hull of the feasible solutions here, the integer feasible ones. And it turns out that you can do this. And this is one of the IPs or linear programs that we came up with based on prior research, I have to say. So again, same objective function. We maximize gains from trade. And what we do here is, and that was also not a new trick, we introduce a variable for each and every possible allocation. Okay, so this is delta. This is many, right? So this is Stirling number of the second kind, so this explodes on you. We are in theory, we don't care, right? So we have this additional variable. So, but at that point, we make it a really huge linear program, right? So these are constraints that essentially say just, well, if a particular item gets assigned or package gets assigned, then this has to equal the sum of all the weights of particular allocations that have S as part of it. Same thing for the sellers. Then the usual constraints that we've had up there. And then all the weights of all the particular allocations that are possible add up to 1. So you want ideally to select one allocation. And what you can show is that this linear program would always have an integer solution, right? Why is that? So this constraint says there's going to be at most one, but it could still be fractional, right? So these weights could be distributed among many. But the objective function is such that it ensures that the allocation maximizes gains from trade. And the integral extreme point is such that it's going to be, there is going to be at least one integral allocation that we have to choose with this linear program. So this has nothing to do with total unimodularity. This is just a specific argument for this very linear program that, given the way how we cast the objective function and how we set up this problem, the linear programming solver will always force, or can be forced such that we pick an integral solution, right? So this is nice because if all the delta, the weight, is on a particular allocation, I know that all the bundles that I assign also have to be integral, right? So I have an integral linear program. The downside is just it's huge. But if I go, yeah?
But
it's not unimodular. But it has yes, it's just I buy. So I can solve this with a polynomial time algorithm, but I buy this by an exponentially large formulation. Okay. And now we can take a look again at competitive equilibrium, because now if I have integrality, I can use the same trick as before. So a competitive equilibrium in this model is a feasible solution, say the optimal solution that we found by solving this. And again, if I draw on the duals, I can just state that at the prices that I'm gonna derive, the buyers and the sellers, they maximize their payoff. So that's, and a third constraint that we want to have for a competitive equilibrium is that the market must be balanced. So in the sense that what the money that the buyers put on the table is what the buyers get. So there are no subsidies. If this is the case, we call it a competitive equilibrium. Okay. And again, what I alluded to before, I'm not super formal here, is the core is the set of feasible allocations that cannot be improved upon by a set of coalitions of the economies of agents. And you can show that all possible equilibria, so these equilibrium prices might not be unique, but they form the core polytope. So there are different prices that you can set. Whichever one you pick, it is a core solution. So there cannot be a situation like the one that we saw before, that a subset of buyers and sellers can deviate from the market at those prices. Okay. And now let's take a look at the dual, and it looks very familiar from everything you've seen so far. Again, we have these constraints here. These are the corresponding primal variables. So if I have an optimal assignment, then these are tight, and buyers and sellers maximize their payoff. And I have a third constraint now, which is this one, which is essentially what buyers pay has to be equal to what sellers get plus pi a. What is pi a? This is the constraint of the very last, or the dual variable of the very last constraint, and this can be interpreted as essentially what the auctioneer makes, right, or what he puts in the market. So if you take a look at this here, these are now the competitive slackness conditions, and this is now this additional constraint that is reminiscent of this definition of competitive equilibrium. And already by now you can see there can be situations where the buyer needs to chip in money. Right? The auctioneer has to provide some money, the market operator. I've already shown you an example where this is the case. VCG is a good answer in general. The VCG is not budget balanced, but you remember the example that I showed you before where there is no competitive equilibrium. This is a situation where the auctioneer, in order to make it such that nobody would want to deviate, he has to put some money into the market. Right? Why am I telling you all this? Well, that's actually what's happening in US electricity markets. There are uplift payments, right? But we will get there. Right. So this can be formulated as a proposition saying that the assignment X star and Y star and the prices Pi star and Pj star derived from an optimal solution to this huge linear program are an optimal solution of the primal and the optimal solution of the dual for a competitive equilibrium for the model primal if and only if pi a is null. So if I can find a solution that the auctioneer does not have to, he doesn't gain money, but he also doesn't have to put money into the market, then it's a competitive equilibrium. Yeah.
Do we have a condition when pi is positive, when negative? I know negative is a problem, but what about when it's positive?
So pi a, you mean?
Pi a.
When it's positive, he would make money, right? Let me think about it.
Do we know under what conditions it's positive or negative?
I don't know of any work that would go into that. So the main cases that I can recall is when, in order to make it positive, he would. So it's a variable that can be positive and negative. You might have seen in before. So it's here. It's not. It doesn't have to be positive, but
They are positive, sometimes negative. Maybe they can balance out over time.
over time. Okay, that's we are looking at a single market at a single point in time where we want to satisfy all of this. Yeah. Usually, and I'll get there in a minute. It's going to be negative in the sense that the auctioneer has to give money into the market to satisfy that nobody would want to deviate, that we have a stable outcome. Right. Actually, my suggestion is, I think, where are we? We are an hour and 10 minutes. Maybe this is a good time for a break? Okay. Then how much? 15 minutes, and then we would reconvene here, and I promise I'm gonna get a little bit more practical in the sense we go back to linear prices and actual real electricity market design. Okay? Good. Thank you. Welcome back, everyone. So let's get started again. And thanks for all the many questions in the break. Great to see that there is some interest. Very good. Let me just revisit where we left off and just make clear what we did there. So as a brief wrap-up, what I showed you a very simple market problem at the beginning, which was this assignment problem, where we got all the nice economic properties that you usually would expect from a market. Right? So even strategy proofness, which for the rest of the lecture I'm not going to talk about. Then we made this model a bit more complex. We relaxed some of the assumptions, in particular unit demand model. And what we found is that finding these competitive equilibrium prices, which you can think of as the dual variables so far, is a little harder. We needed to make additional assumptions. In particular, one that stands out in the literature is this gross substitutes or strong substitutes condition, where you get integrality and then you can again leverage the duals. Right? Then in the second part, we looked at a particular allocation problem where we have these block bits, very similar to what you have in these energy markets today. And we saw, okay, it's a non-convex problem. And we were asking, in theory, is there a principled way to get to maybe nonlinear and personalized prices when they exist? And the way to do this is we went through, we started from this standard implementation of how you could implement a double-sided combinatorial exchange or double-sided allocation. And then we strengthened this model, right? In a way, we looked at an extended formulation. And what we did there was really we added a lot of variables, right? These delta variables for each and every possible allocation, which makes the whole formulation impractical. It would be way too large. So what we did, we traded in computational complexity with space complexity. Right? But that allowed us to get back to a linear program, and what we got was, we actually, out of this, we get competitive equilibrium prices if if we have a solution where pi a is null, where the auctioneer does not have to chip in money on this market. Okay? So that's where we are. And by now, at the break, you might have thought, okay, now he's going theory, and maybe it's not relevant anymore. So let's get back a little bit to something that is a bit more more practical. Where were we? So I think I convinced you this is a principled way to get to these nonlinear and personalized prices. But is this really what we want? So this comes with some downsides, right? You had an Austrian speaker in the morning. You have an Austrian speaker now. Of course, I'm going to cite an Austrian economist who's going to be Friedrich Hayek, and he became fairly famous with an AER article, so American Economic Review. One of the citations that I took from there is the most significant fact about the price system. I added price here, by the way, is the economy of knowledge with which it operates, or how little the individual participants need to know in order to be able to take the right action. So he was making an argument for a market economy. And he said, well, this is beautiful. I mean, I have maybe thousands of different products. I look at the prices. I only need 1,000 numbers, but then I can make an optimal decision, right? So isn't that nice? I was just showing you, well, in general, that's not true because you need 2 to the 1,000 prices, right? So that's not going to be very helpful on that end, right? So that's not what Hayek had in mind when he talked about the marvel of a market. And by the way, this paper, The Use of Knowledge in Society, is still one of the most important and influential papers in AER in its history, kind of. So maybe let's get back to linear prices. Maybe we don't want to give up linearity, so one price per item. Because these exponentially many are in a way impractical. Why do I say that? Well, if we had linear prices, we have a very simple interpretation, and it's very transparent, right? So if you have a day-ahead market, you have 24 prices for each hour of the day, or now times 15 for the smaller market time units. But this is kind of readily interpretable. This is the basis of derivatives, right? If you have exponentially many prices, how would you do a derivatives market, right? And there is also a different notion of fairness that people have in mind, which I realized by other applications, which is very likable about these linear prices, in the sense that suppose two sellers sell the same package, right? An hour of energy in the morning and in the evening, say, whatever. They should get the same revenue, right? With personalized prices, there is no guarantee that this would be the case, right? So a couple of arguments why you might not want to deviate too much. So what can possibly go wrong? So here is the simplest example that I could think of why linear prices destroy something. So suppose I have one seller who sells this package of two identical market time units, say, and he wants $30. And then I have buyer one who is willing to pay up to $10 for one item, and buyer two willing to pay up to 26. So it's pretty clear there are gains from trade, right? Because they put 36 on the table, the seller only wants 30. But it's also clear if I have anonymous and linear prices, I charge both of them the same, then there's going to be no trade, right? Because I can only set a price of at most 10, so buyers only put 20 on the market, so that's not enough to satisfy the seller, right? So there is an efficiency loss, right? Simplest, so just to make it as blunt as possible. That's not the only thing. Some of you might have heard about paradoxically rejected bids on markets. I see some nodding, that's good. So here is a simple example what that means. Suppose I have one seller who is selling 3 A's, right, for $60. I have these 3 buyers, they all want 1 A, and they are all willing to pay up to 30. So they put 90 on the table, the seller wants 60. That's great. So we could match them and satisfy this one seller. But if we have these linear prices, so for example, we could set a price somewhere at 25. They all make a profit, but look at this second seller. So he is willing to sell 1A for 10, so much cheaper than the 20 that this seller would charge per item in a way, but he would not get matched, even though he's cheaper. Right? This is what is referred to as a paradoxically rejected bid, and that can happen because the welfare, if we match those three with this first seller, is obviously higher than if I match any one of those with seller 2. Nodding? Okay. And now we are getting a little more real world. So this is actually a concern in day ahead markets, right? So we do have these paradoxically rejected bids, right? Right. So the good news is there is an old insight in economics. If markets grow larger, they kind of convexify to some extent. And there are different ways to make this precise, this statement. This is one proposition we once derived, and I thought it kind of fits. Suppose we have a multi-unit market, so we have the same type of goods, but multiple units of it, with one seller selling a package of K units, and n unit demand buyers, and the valuations of buyers and the sellers are drawn from the same distribution. So this proof uses order statistics, and we assume that the distribution is the same on the buy side and on the sell side. Then the expected efficiency loss due to linear prices is less than k minus 1 divided by n plus 1. So what does this mean? Very intuitive. If the packages that are being sold are getting smaller and smaller, or if the number of bidders grows, then the efficiency loss grows small, right? So just have more and more bidders, then you can expect that the efficiency loss is getting smaller, right? Or if the packages that you ask for are not very lumpy, not very big block bids, then this is also good news, right, for efficiency. So this is one example of an experiment that we ran on some other data where you see kind of the efficiency losses for a particular data set, and you see that on average they grow small to less than 5% for this particular market. This was a market for fishery access rights. There are some papers who actually looked into this for the European day-ahead market, and they also found efficiency losses due to these linear prices are actually not so bad. But, you know, you have to be very careful when to interpret these numerical results, right? But in general, there is reason to believe if a market grows very large, then this efficiency loss might not be so heavy, and if it's not very lumpy, all right? And I think that's the main conjecture why we do in Europe what we do, kind of, right? So it's kind of good enough, right? And that brings me to this, I think, key distinction between European and US electricity markets. So Jalal and I just talked a little bit. So what I told you so far is pretty much what's going on European electricity markets or the European day-ahead market. You go with a suboptimal solution. So essentially these prices, these linear prices, come in as constraints. And they might... So the welfare gains might be lower than what they would be without these pricing constraints. So if you would allow for non-linear prices, you could get higher welfare, right? But that's not what we do in Europe. We enforce these linear prices and take into account that welfare might not be optimal, right? And that's what Euphemia does, right? So we don't have any side payments, but we do have these paradoxically rejected bids, right, that I was talking about. And that is different to what they do in the States. So in the States, they go for the efficient solution. And whenever I talk to colleagues in the States, they would say, why the hell do you give up efficiency? Isn't that, you know, from an econ point of view, the primary objective, and everything else comes after? So here you really aim for the welfare maximizing outcome. But the market operator has to pay some uplift. So you saw this pi A before. Think of it that way. So in order to make these markets stable, if we have the efficient solution, there has to be some third party that gives money to people that they don't deviate from the solution, right? And of course, real-world electricity markets are way more complex. So there are different types of bid languages and whatnot. But the only thing that I want to achieve today is really help you understand what are the fundamental problems that you can't, you know, fix with some heuristics or some smart ideas that are there. And I think that the bottom line is it's the non-convexity that makes these things so hard, right? Good. So let's take a look at these, what the US American ISOs do in general. And I learned that a few of you are actually working on convex hull pricing, which is great. So this was a proposal that goes back to Hogan and Ring in 2003 on convex hull pricing and ELMP. So this is a particular instantiation for a particular type of dispatch model. Is essentially, you can think of that version as you take the duals of the relaxed optimization problem, kind of, right, as prices. And we've seen the issues that come with it, so they might not be exact competitive equilibrium prices, but you know, if the integrality gap was small enough, then you could go with it, right? So this was the first proposal. MISO, one of the ISOs, is using it. Most ISOs, independent service operators in the States, use IP pricing. So the approach here is different. This goes back to work by Dick O'Neill, Ben Hobbs was on the paper, a couple of others, published in eJOR. And what they do is, let's first determine the optimal solution with an IP. So, and then let's fix the non-convex variables, like the unit commitment variables. So the xi in the UECD that I showed you before. And then what remains is a linear program, right? And then let's take the duals of this remaining linear program. That's IP pricing. And that's ultimately the recipe underneath most ISOs and how they set their prices. Okay? Before, you've seen we had this optimization problem, and if we had a convex one, the prices just fell out of it. We didn't have an extra calculation, right? So we just took the duals. So here, just to make sure, we first do the clearing, and then we solve a separate problem to determine the prices. And we solve them to find prices in a particular way. Namely, we want to minimize. So essentially, we want to minimize kind of the money that we have to put on the table as a market operator, such that the individuals do not have an incentive to deviate with what they have to pay, right? So what Hogan and Ring, and I'm not going to go into every detail here, are essentially trying to do is this global lost opportunity cost. So suppose I was telling you a competitive equilibrium is such that if I look at what I get and if I look at the prices, I wouldn't want to have anything else, right? Global lost opportunity costs are, well, I can't guarantee that due to the fundamental problems that I was showing you. So, okay, I give you some money, right? Such that you don't have an incentive because I know that there is a better allocation maybe and a better price that you would, so you do have an incentive to deviate. So let's minimize these incentives. Okay, and for that, I need to put money on the table as a market operator, as this third party, right? And that's what you minimize, and you try to mimic in that sense a stable outcome, right? So, well, you achieve in a way a stable outcome, but at extra cost. That in a competitive equilibrium, you've seen the definition before, that does not qualify as a competitive equilibrium anymore, right? So, what is actually being done in these markets is not that all the global lost opportunity costs are paid out, right? So what you pay out, at least in most of them, so it's a very diverse landscape, is the make-whole payments. So it just pays so much that you don't make a loss, right? And if you still deviate, you know, I penalize you, okay? So it comes with a penalty in a way. And that should enforce stability. So, okay, I know that you have a possibility to move to, you know, produce more or less. But if you do that, I want to make sure that you don't make a loss. But if you do that, then you incur a penalty, okay? So what are possibly issues here? It's interesting to see there was an order by the FERC, the US-American regulator, a couple of years ago, and they said these side payments, or sometimes they refer as uplifts, you might have seen. This is mostly what they refer to are the make-whole payments. They can sometimes be really large, right? So for some of the generators and participants, they can be huge. And this really obviously distorts the price signal that you're giving on the market. So ideally, you would have a price that kind of mimics marginal cost, but that's far away from it often, right, for particular generators. And this is a fundamental problem. I hope you understood by now. And then when I wanted to point your attention to another paper by Shiro in 2015 that I think is interesting, that looks in a bit more detail on convex hull pricing, which is kind of the gold standard I think in the economics or electricity market literature. And one of the things that they point out there, which is I think by now a well-known issue, is that the congestion prices might be wrong. So what do I mean by that? So you have a price on one node, there is a link to another node, there is no congestion, yet the prices on these two nodes are different. This is something that can happen with, and vice versa, with convex hull pricing. And I think this is one of the arguments why many people use IP pricing, or many ISOs still, because with IP pricing that's not the case. What does IP pricing ultimately do is they minimize local lost opportunity costs. So sorry if I have to overwhelm you with many new terms. What does that mean? So I stick, and that's essentially what IP pricing does. I stick to the commitment decision that was made. And then I just say, okay, I'm committed, I know, I have to produce, but I still can vary and deviate from how much I produce, from what the market solution would be. That's a local incentive, right? So I take it as given that I'm either not committed or committed, versus a global lost opportunity cost is, well, I can move to a totally different allocation at these prices, right? So I'm not committed and might all of a sudden generate, right? Things of that sort. So, and it turns out that if you minimize these local lost opportunity costs, which is what IP pricing does, then you get appropriate congestion signals, right? So, which means again, if there is congestion, there can be differences in the prices of different nodes. If there is no congestion, there is none. Okay. So these are kind of two downsides. One of the things that we did a couple of years ago is we looked at it and said, well, these are goals that are at odds. And one of the things that you can think about is, well, let's take a look at both of it and take a multi-objective optimization point of view. So we called it the join rule. So this is in an OR paper. One of the things there, and what we do there is we minimize the maximum of either the make-whole payments or the local lost opportunity costs. You could also do scalarization and weight these objectives. So again, what you do in all of these pricing rules is first determine the optimal clearing, right? The optimal allocation, and then determine the prices, right? And what convex hull pricing does is it minimizes global lost opportunity cost. So you could also go there and say, well, I don't care because penalties I have to pay. Why don't I minimize the make-whole payments just? And you can see actually, if you do the numerical exercises, that then all of a sudden really what the market maker has to pay becomes very low. But it comes at an expense, namely the local lost opportunity costs. They are not in the picture. They can be very high. So these guys have very high incentives to deviate from the dispatched solution, right? And what we do is we try to keep an eye on both objectives. And here is a little numerical example just to make this a bit more digestible. This is a specific example, a particular day that we cleared. These are the global lost opportunity costs if we do ELMP, so this convex hull pricing. This is the result with IP pricing. So as promised, the local lost opportunity costs are 0, but the make-whole payments are fairly large. I can do the opposite. I can just minimize the make-whole payments. Then those are 0, but the local lost opportunity costs are very large. But I can also find a sweet spot between those two, and this is the joint pricing rule that takes both of them into account in a particular objective function, and then you find a solution that has fairly low local lost opportunity costs and fairly low make-whole payments. And from an operational perspective, that could make sense. At least we got some positive feedback from people in the field, right? Good. Right. There is a lot of other things. So what I like about it, and Jalal and I had a nice discussion yesterday evening, electricity market design is a very rich area, right? So what I focus on in my talk is really what are fundamental issues for which there is just no simple solution and you somehow have to deal with it. And then there are many engineering questions that come with it on top of it. But also, it really leads to kind of new and interesting questions in market design in itself that you don't find necessarily in other domains. So one of the things that we looked into, just to give you an idea, think about it, these mixed integer programming problems like the DCOPF that many of you are working on, there are an approximation of the real underlying power flow problem, right? So what you actually want to solve is an ACOPF, but everybody knows, well, this is a non-convex, non-linear thing. It won't scale to sizes that we are interested in. So, and there's been a lot of really interesting research out of the optimization community on convex relaxations. I think some of you might have looked into SOCs or QCs or SDP relaxations. They come at a cost, in particular also when you take binary variables like commitment variables into account. But they are also, we've seen a lot of progress in the recent years. So this Go challenge that Dick O'Neill and ARPA-E kicked off is a nice view how powerful research progress was in that area. And one of the things we did is saying, well, maybe we can leverage this also for pricing, right? So if we have a better kind of relaxation of the real problem being the ACOPF, then maybe we even get better prices, and you can actually show so. So if maybe in the not too distant future for some electricity markets we move to something different than these mixed integer programming problems, we might also get better prices, which is kind of neat. We had a paper more recently where we looked at very large problems of that sort. So before the break, we talked a little bit about these 15-minute market time units, which led to a much larger mixed integer programming problem. And as a matter of fact, people are having difficulty solving this in time, right? So there are some ways that come out of actually economics research and ideas on how we can use convex relaxations in two price vectors. One would be for the buyer, one for the seller, but it's still linear prices and how you can clear markets with essentially linear programs, right? So you move away from a single price vector, but you get a lot in terms of the size of problems that you can solve, right? So for example, if Europe would move towards nodal pricing, of course, the problems get even larger because you have to model all the constraints in this market, and you need an appropriate description of the entire grid in Europe. So it's not clear how that these problems can be solved in the time that is given on a day-ahead market. So there are, I think, interesting tricks on how we can maybe move on and solve larger and larger problems of that sort. Right, so one of the things that we are actively working on is robust clearing. So with more and more renewables, then you have to make a dispatch decision without knowing what the real realization would be, right? So many people have looked into robust clearing. Well, that leads also to questions on how do I do the pricing then, right? So this is, I think, a really interesting question. This is one of the questions where I really think this doesn't pop up so often in other domains, right? If you look at transportation or so. So this, how do you handle uncertainty, right? If a constraint is maybe not even binding because you just don't know the real parameters of the problem yet. So I think this is something where there's a lot of research going on right now. And it's good that I've been asked before. One of the specific aspects of electricity markets that I was hiding under the rug is essentially we don't have a classic combinatorial exchange, right? Why not? Well, actually, we run these markets on the grid, right? So we essentially have a market on a particular network node, and then if there is excess supply, we can get this excess supply over to the neighboring node. So it's a networked market or a coupled market, right? So that's also something that is very different than in other markets that we have, where, so if you have a transportation market, you just collect asks and bids, but there is no network structure that you need to consider. Well, that's different here. And one of the questions that I got during the break was, oh, okay, so you're telling us that under certain assumptions you get efficiency, but isn't there something lost if you take this network structure into account? And fortunately, I have a slide. The point is, you can actually prove that as long as you have convexity of the underlying cost functions and demand functions, then this comes without loss, right? So this means you can recreate or restate the welfare theorems and get the same results. So you're actually maximizing welfare, even though it's a networked market, right? So let me just read this off. Suppose that the cost and value functions of a market participant are, in a coupled market are convex. Coupled really means, again, nodes are interlinked, right? Let price vector P star and the allocation Z star be a valuation equilibrium, then this allocation maximizes social welfare. And conversely, if Z is a welfare maximizing allocation, then there will be a valuation price vector that supports this allocation that then forms a valuation equilibrium, right? So valuation or valuation competitive equilibrium again refers to these specific competitive equilibrium price vectors that we had on the slides all along. And this is kind of neat to know. So the efficiency losses really just come from this non-convexity, not from the fact that we have a network market, right? And that was not in the literature, at least to my knowledge. So we use a specific proof technique for that. But what I want to emphasize is I don't assume continuity. So it can be, discrete convex functions, right? So stepwise linear functions, the demand or cost function, that's all good. The only thing we need is convexity. Okay. Good. How am I doing in time? So half an hour more, something like that. Okay, 40 minutes. Great, perfect. Any questions up so far? Because otherwise I would drag you into the ugly part. Okay.
I had a question for, you said that when you have linear pricing in prices in markets like the European markets, there was an efficiency loss that kind of lessened when the markets got bigger.
Mm-hmm.
But is there the same effect with the uplift payments if you have these the United States clearing? Because the markets are quite a bit smaller there.
Okay, so first of all, what the US Americans do in all the ISOs is they really go for the welfare maximizing outcome, right? So that's maintained. You're alluding, I think, to the fact that these are smaller. That's true. So I think the European market is kind of unparalleled in size. But even if you look at something like Kaiso, it's a decently sized market. I haven't seen studies where they really look at the efficiency loss and try to estimate what it is. But I mean, as a matter of fact, there is no real efficiency loss because they definitely pick the efficient outcome. It's just what they pay for it is these uplift payments. And that is an issue. This is essentially what I try to bring out here, right? So.
Do the side payments, do they scale with the market size as well?
I'm pretty sure they would. So as I said, so if you have larger and larger markets, these markets convexify, but it can still happen that, say, for one market participant, you have to pay a very large uplift. And that's kind of what worries them quite a bit. Even if you talk to people like Dick O'Neill, who has been in this game for, I don't know, some 40 years now, he would say, this is something we need to think about. And he actually has still ongoing work on this. So because these uplift payments are a bit worrisome. Yeah.
You had a slide with your proposed method for make whole payment and this one. So can you show us these numbers but not prices? To what extent prices in each item are equilibrium supporting?
So none of these rules is really a competitive equilibrium, right?
Do we know how much?
Well, I think an estimate is really kind of how big the global lost opportunity costs are, or maybe this is a good overview, kind of, right? So I think if those are high. The global lost opportunity costs, you could argue, are fairly far away. On the other hand, maybe that's not the decisive issue. I think one aspect that is also specific about electricity markets is the very fact that, well, stability is actually not so hard to enforce in the sense that if somebody deviates, you can observe it, right? And you can penalize them. That's why I highlighted penalty here. So essentially what you worry about most is really the make-whole payments, because obviously you don't want generators to make a loss, right? And that's what, so we had some work where we said, okay, if this is what they worry about, just let's minimize that, right? But again, it comes at the cost of then very high local lost opportunity costs, which is also something that you want to avoid. So this seems to be a trade-off that is there that was not in the literature that we thought is kind of interesting and that can be exploited to maybe improve a little bit on what we have right now. So it's kind of, it's not a made up, it's a real issue. And you know, if you talk to Ben Hobbs or Dick O'Neill, they would all agree on that, I think. Okay. Okay. Anything else so far? Yeah. Are you talking about the robust clearing? Oh, okay. Yeah. Absolutely, and it depends very much on what robustness objective you choose. So is it worst case regret, or you know, are you looking at regret at all? My suggestion would be to stay in time. Maybe let's take that offline, because that would be a whole separate talk, right? So if you talk about robust optimization, you get into a wealth of other issues which maybe derail us a little bit now, but I'll be happy to talk to you about that afterwards. All right? Good. So I think the last chapter that I wanted to convey to you is really, if you make one very reasonable additional assumption, namely that if people have budget constraints, then things become really incredibly hard, right? And that's a bit surprising if you think about it, because it's a very reasonable way to think about markets. Well, maybe not everybody can pay up to any amount, right? So if there is another crisis in the Ukraine and gas prices skyrocket and then electricity prices skyrocket, you might not be willing to pay each and every price, right? And maybe it might be nice to have a cap, right? To say, well, okay, this is what I'm interested in, but in total I'm not willing to pay more than X on this single day, things of that sort. And there are a few papers who kind of start thinking about it. And I think the last chapter or the last message I want to convey is, well, if you put these budget constraints on top, then things become really ugly, right? So, yeah, again, just a bit of motivation here. A buyer might value electricity highly, but only up to particular expenditure limits. And high scarcity prices can make otherwise efficient demand infeasible for budget-constrained buyers. So the type of utility function that we've been looking at all along is this quasi-linear utility function, right? And now we put this constraint on top. Okay? That should be, so this is the budget cap of a particular buyer B, and this is the price that he's going to pay. And again, this looks fairly innocent, right? And obviously, economists are also aware of budget constraints sometimes play a role, even if you have efficient financial markets. So it can be a very practical issue. So let's see what these budget constraints do to our pricing problem, right? So that's the question now. So I want to start out with a simple example just to say the obvious, right? And this is the example that we have now. Again, A, B, and now we have a budget constraint. So forget the budgets here for a minute. If there were no budget constraints, it's pretty obvious you would charge a price of maybe 2 for A, 2 for B, and then sell the package A, B to buyer 1, because he has the highest willingness to pay, and that would be stable, right? So it's super easy. Now I impose a budget constraint on the guy. So he can only pay up to 3. And it's pretty obvious, well, assigning A, B to buyer 1 would not be stable anymore, right? Because why? Well, at least one of the items would have a price of less than 2. So there can always be a coalition that deviates, right? So just to make it explicit, if B2, if I charge €3 to buyer 1, then you know, depending on how exactly I set the prices for A and B, a coalition of B2 and A and B3 and B could deviate very easily, because in total he is only able to pay 3. So that's the obvious. So in the stable solution would actually be to pick the allocation that does not maximize welfare gains, but to assign A to B2 and B to B3, right? That's stable, but you know, of course, if you look at welfare only, it's maybe not what you want. So there is this basic tension. Okay. So that's the superficial insight that is maybe not so earth-shaking, right? There is a much more fundamental issue. If you remember at the very beginning, I was telling you about quasi-linearity and welfare maximization, right? And that if I am in this quasi-linear world, where, remember, €1 is worth as much to me as it is to you. Right? So that's the main ingredient, the main assumption that is underneath. And I was giving you this Elon Musk example, saying that that doesn't necessarily hold. This is what kicked off the whole Arrowian social choice literature. Right? So as a matter of fact, if you have budget constraints, that assumption becomes a bit brittle. Why is that? Suppose we both have the same budget limit, say €1, right? If I get an epsilon more, I could become winning. So, I mean, you can easily construct examples where a marginal, an epsilon is, and make a huge gain, for example, right? Where having an epsilon more money beyond the hard budget constraint gives me a lot of wealth, a lot of payoff, and it's not comparable anymore, right? So the marginal value for money with budget constraints is something that is almost a philosophical topic, right? So, and we had this insight that you find in textbooks like Mas-Colel or Varian saying, well, as long as we have quasi-linearity, maximizing aggregate surplus, which I often rephrase as utilitarian welfare, if you go to the philosophical origins of what lies underneath, then this is a Pareto, leads to a strongly Pareto efficient outcome. So there is no one who can be made better off without making somebody worse off. What I'm telling you now is, well, with budget constraints, you have to be very careful, right? So maybe that doesn't hold anymore. Right. So let's start from first principles. That's, by the way, the reason why, if you look at economic theory literature, they rarely talk about welfare maximization. They talk about, in a way, you could say weaker criterion. We want Pareto optimality, right? So there are two versions of Pareto optimality. One is weak Pareto optimality, which is here mu is a particular allocation and p are the prices, right? So weak Pareto optimality just means there is no other allocation mu prime and p prime such that everyone in the coalition could be made better off, right? So then I call it weakly Pareto optimal, right? Strongly Pareto optimal, and this is usually what people strive for in this literature, is a bit different. It says there is no other allocation. If I pick one that is strongly Pareto optimal, I can be sure there is no other allocation and payments such that everyone weakly improves, so they might have the same payoff, but at least one has a strictly higher payoff. If there was such another allocation, mu prime and p prime, the allocation that I'm talking about, mu and p, would not be strongly Pareto optimal. Okay, so this is something I can compare without having this additional, or that I can look at without having this additional assumption that $1 is the same for you and for me. Okay. All right. So this is what people look at. Simple example. We have one item. We have two buyers. One has a value of 1. and the other has a value of 2. No budget constraints yet, right? Trivial solution, of course, give it to the guy who has the highest payoff, right? Or the highest value of 100, charge a price of 1. This is strongly Pareto optimal, right? So because there is no way to improve one. There is no other allocation that could make others at least weakly better off and one strongly better off. Now I assume I have a budget constrained 1. So there is this first bidder who has a value of 1, a budget of 1. The second bidder who has a value of 100 and a budget of 1 as well. Okay. So I have 2 feasible outcomes, and they are both in the core. So there is no coalition that could deviate. So the first one is I give the item to the first bidder with the lower value. Then both of the bidders, 1 and 2, they would both have a payoff of 0, right? So the seller gets €1, both bidders. So the one says, well, I have had a value of 1, I pay 1, so my payoff is 0. And the other doesn't get the item, so it's a value of 0 as well, right? If I reallocate this one item to the second guy, well, then I have a Pareto improvement, right? So the first bidder still has a value of 0, but the second bidder all of a sudden has a payoff of 99. And the seller doesn't care, he gets €1 anyway. Okay, so that's a Pareto improvement. Right? And what you can actually show is, let me maybe move here. You can make this statement more broadly, and you can. So far in the quasi-linear economy that we discussed so far, it was welfare maximization was a necessary condition for strong Pareto optimality. What we can say now is at least it's a sufficient condition. So if I take the set of all possible core allocations, here I have 2, I assign the one item to the first or the second bidder, both are in the core because there is no coalition that could deviate, right? Where both are better off. But if I take a look at all the core allocations and pick the one that maximizes welfare, then it's a sufficient condition for strong Pareto optimality, right? So just one sec. So what I'm saying is, at first sight, if you think about it a bit more carefully, it's not that obvious that maximizing utilitarian welfare as we did is the right thing to do in these markets if you have these budget constraints. Because this basic assumption saying, well, €1 is the value, has the same value for all of us, it might be challenged, right? But we can at least say, well, if we do this, then you definitely get a strongly Pareto optimal outcome. So which gives us a principled rationale to do this, right? You had a, yeah?
Sorry, I have a naive question. So what you're saying is that buyer 2 says, I want this item, the value of that item for me is $100, but I only have $1.
Exactly.
Do we have such kind of market in reality?
All the time, right, when you have budget constraints. So if, I mean, think about, I've done a lot of work on spectrum auctions, right? So the net present values of a block of spectrum for 15 years is huge, but your CFO might not give you 10 billion, right?
Doesn't it motivate me to say that, okay, the value of good for me is $1 million, but sorry, I have only $1.
Well, I'm not talking about strategies now, right? So, okay, there are always 2 views that I can have on a market design problem of that sort. One is I have strategic bidders and one are non-strategic bidders. So let's assume the strategic aspect away. That's why I always talk about non-strategic bidders, or the way I phrased it was bid takers, right? So suppose we have complete information in game theory. I know everything. Is it even then possible to find an allocation that is nice, right? And, you know, we could have a very long discussion about incentives. We all know these day-ahead electricity markets are so rich, so, you know, you're solving some MIP with hundreds of participants. How would you game it? You would need to know a lot. I'm not saying that this is impossible, but I'm saying for this discussion now, let's leave out the strategic aspect. Right? Let's assume people are truthful for a minute, right? And what I'm saying is even then it's hard, okay? Good. So I've now given you an argument why we should still keep on maximizing aggregate surplus or welfare, right? But I'm getting back to incentive compatibility now. You remember the first example that we started out with? That was the assignment market, and I hope I could convince you, hey, this is great. This is a market where you have even group strategy proofness. Are you throwing things at me? So we got incentive compatibility. And now I'm going to give you the very same model, and I just impose this budget constraint on top on the buyers. And I'm going to tell you, actually, incentive compatibility is gone first inside, right? And it's actually a fairly simple proof. I tried to sketch it. So it's kind of a counterexample. Suppose I have 3 bidders, 1, 2, and 3, 2 items, A and B, and they all have a value of 10. All 3 bidders want A and B for 10. They all have a budget constraint of 1 for the sake of it. Okay? And then if bidders report budgets truthfully, there will be 1 bidder who goes home empty. Of course, right? Without loss of generality, let it be bidder 3. Right? So what could bidder 3 manipulate in this situation? Well, he could say, actually, my budget is higher. It's 2. Okay? So he lies. And then I could try to assign this additional item, or the second item, B, for example, to bidder 2, and to bidder 3, and bidder 2 goes home empty. However, if I look at this core or competitive equilibrium definition, there must not be envy. And the point is, in a core solution, if I have these 2 items, or 2 units, they need to have the same price, because if they did not have the same price, there would be a coalition of one of the sellers and the buyers who could deviate. So there would be envy. And so I'm forced to have the same price in this specific case for both items. But if I do that, then I can't do anything about bidder 3 to lie to me, right? So because, I can't force him to be truthful. So there is no incentive to be truthful. So this is a kind of a little counterexample that this type of manipulation cannot be avoided. So at least there are specific situations where there is no way how you get this a truthful mechanism, right? And that's kind of the first insight. So something that was given, admittedly, only for the unit demand case, the assignment model, is all of a sudden not granted anymore, right? Which is a bit of a pain. But we didn't have incentive compatibility anyway throughout the whole discussion, right? We just assume people are truthful because you would need to know way enough to manipulate in a reasonable way. That's not always true, but let's stick to this assumption, right? So what we can still do is we can impose another assumption, and then we get back all the nice properties. So what we do in the paper is we use this, you remember I had this ascending auction algorithm at the beginning by Dimanche, Gale, and Sotomayor, so the Hungarian algorithm, and we can run something like that. This would be way too complicated to tell you every detail, but let me highlight a few things. So this works exactly in the way how I showed it to you at the beginning. But then if somebody drops out because he had a budget constraint, then we have a price vector of 2 and 2 here, so 0, 0, 1, 1, 2, 2. Then I see, oh, the guy dropped out, and it had to be a budget constraint. Why do I know? If 1 was the value of this guy, then at this stage where he would have been indifferent to the empty set or the budget, right? So you might argue this is a bit of an artificial assumption, but at least in theory, if the bidders are truthful, that's what they will tell me. Here he says, well, actually, I'm still demanding it, but I can't afford it anymore. If I can make this distinction, and you can challenge that, then I can understand the guy dropped out because he had a budget constraint, and then I reset the prices. So I drop him from the list, I reset the prices, and then I find a perfect matching. The lady gets the banana, and the other lady gets the apple, kind of, right? So what I'm saying here is the very simple ascending auction that I showed you at the beginning with some mild tricks can also be extended such that whatever comes out is a strongly Pareto optimal solution under a single assumption. And that is important. That comes now on top of the unit demand. Namely, in a single round, there must never be two bidders who drop out at the same time. Why is that? Because if there are two, as an auctioneer, I cannot decide which one I would keep in the auction and which one I would remove. Right? So essentially, and then you can construct examples where welfare is arbitrarily bad. Right? So, and that's kind of an additional assumption on unit demand. So if I have unit demand and if the values are such that the bidders would never drop out at the same time, or more than one would drop out at the same time, then I recover all the original properties of the Dimanche-Galian-Sotomayor algorithm. But if not, then I can't say a lot. Right? So, and yeah, so this is kind of, if you argue unit demand is already a strong assumption, you would probably be with me that when I say this additional assumption is even stronger. So it's, I'm just telling you, I have to make a lot of assumptions to recover the good properties of a market. Okay. So if I don't have this assumption, what can I do? I can try to write this problem up as a linear program, right? So let's try to maximize payoff. So this is what you see up here. So this is the sum of the utilities. Here is a constraint that describes the utility of the buyer, a utility of the seller. These are binary variables here. Each buyer can have at most one item. Each seller can have at most one item. This is the budget constraint here. So I say for the buyers, the prices have to be less than either the value or their budget. And these two constraints, they enforce stability, right? So it cannot be that either the buyer, that both there is an allocation where a buyer and a seller can deviate and have a higher payoff. So this is what I avoid with this either or constraint here. So these are also binary variables. Okay. So what I'm telling you is, so this very simple bipartite matching problem that is in each and every introductory linear programming textbooks. If I impose these budget constraints, I can still solve it as an optimization problem, but it becomes an integer program, right, or a binary program. Okay, so that in itself doesn't tell you a lot, right? So it could still be polynomial time solvable. Unfortunately, it's not. So you can reduce from maximum independent set problem and show that this problem, we called it the maximum surplus budget constraint stable bipartite matching. It's a mouthful. So it just says bipartite matching plus budgets. It's an NP-hard problem, right? So you lose both. So without budget constraints, we had polynomial time solvable, and we had incentive compatibility. As soon as we include budgets, all of these properties are gone. So can it get any worse? Unfortunately, it can. So let's now assume we have not unit demand bidders, but we have bidders who are interested in packages, like the combinatorial exchange example again. Okay. So very same scenario that we had throughout. Think again of the European day-ahead market. Bidders bid on single market time units and on block bids, right? But now, suppose we can manipulate or we can change the bid language such that a buyer could say, all right, I'm interested in these bundles. This is my willingness to pay. But in total, I don't want to pay more than X. That's the only change we do. Here comes the bummer. This is a sigma to p complete problem. So this is one level up in the polynomial hierarchy. So even if you had an oracle that gives you the solution to an NP-hardened problem in polynomial time, this would still be a hard problem. And these are notoriously difficult, right? So the way to solve this is, the reduction we have in that paper is a reduction from QSAT. So you might all know SAT is the central problem in among the NP complete problems. QSAT, quantified satisfiability, is the corresponding problem one level up, right? So and it's this formula, does there exist an X such that for all Y this Boolean formula is true. That's kind of the fundamental problem, and you can reduce from that problem to a specific version of this combinatorial exchange with budgets. So this is a no-go, essentially. You can still solve these problems, and one way to do this is bi-level integer programming, right? So just to give you an idea how this looks like, this is again the objective function that we had all along, maximize gains from trade. So just, what buyers are willing to pay minus what sellers ask for. So far, no news. Then I add this on top. So the prices that these guys get, the buyers need to be less or equal to their budget constraint for each of the buyers. Right? Well, and then comes the hard part, because you already see by now what used to be the dual variables is now in the joint pricing and allocation problem. And now I need constraints that make sure that what I get is core stable. So conceptually what you can do, and you can write this up by the way in a much smarter way, is something like, okay, these are the prices that a particular buyer gets. And they satisfy the budget constraint, and they need to be more than what every other coalition can pay. So this is really core stability enforced in a strict way. There are exponentially many coalitions in the number of items, number of bidders, and it's not only a binary, a bi-level optimization problem, it's a bi-level integer optimization problem where the lower level is also an integer problem. Right? So many of the bi-level problems that you see in textbooks, they have a convex inner problem. So these are not. And that's what makes it hard. So there is a very well-known result by Yaroslav from the mid-80s saying that a binary integer so these bi-level integer programs are also sigma 2p hard. Right? That doesn't cover the proof that or the statement that I showed before, because it could still be that this very specific one is not sigma 2p hard, but unfortunately it is. Okay. So the only thing we did, we added a budget constraint, and it destroyed pretty much everything, right? So you might now argue, all right, so we have made so much progress in optimization. Sure, we can solve this. Maybe not in the worst case. In computer science, you're also negative. You also look at worst case. On average, this might be pretty good. Unfortunately, I have to disappoint you. So we actually did that. So we implemented a bi-level integer programming solver, and we looked at a specific data set that has nothing to do with electricity markets, some other fishery exercise markets that we looked into. And just to give you a rough idea, so these were instances with 5 buyers and 5 sellers, fairly small. And we tried to find a core stable outcome that maximizes, again, aggregate surplus, right? So we had 8 instances that we solved. For this problem size, we could solve all instances fairly quickly. If we go to 5 buyers and 10 sellers, we could not solve 2 of them anymore, and we didn't find a stable solution for most of them. And if you go up to 10 buyers and 15 sellers, you're out, right? So, and we ran that on a cluster at some point, but stronger hardware doesn't help you a lot on that end, right? So these problems really explode on you. So this is when we are interested in full core stability. So meaning you're stable against every possible coalition that you can think of. So you might argue, well, maybe this is too much to ask for. Why don't we look at coalitions that only have 3 participants? They could meet in some back room and say, well, we want to collude. Well, then the results get a bit better because you're looking at a much smaller subset of coalitions that you want to be robust against. But also here, if you go up to 10 buyers, 15 sellers, it's gone. Okay. What else could we do to make this more realistic? Well, you could argue, all right, so maybe if we just forget about the true values, let's just take what they are actually willing to pay, right? So meaning, let's rather than taking their value and, and their budget into account, why don't we just look at the capped values, right? So that's what they ultimately can pay. Let's maximize that, right? So what's so bad about that? Well, that destroys your welfare argument. So here is a bit of an exercise that we did as well. So again, very small examples where we could compute everything. 5 buyers, 5 sellers. We can compute the exact solutions. And now we introduced budget caps for different problem sizes. And you see the welfare loss here is in the order of 30 to 40%. So this is substantial, right? So if you say, if I kind of ignore that people would actually be interested in very different products than what they can pay up to. If you just throw away that information, you might, if you care about welfare, pick the really wrong allocation, right? You could, I mean, this is a philosophical question, right? And I see Jalal saying, oh, well, let's talk about this. Fair point, so you could say, well, willingness to pay is willingness to pay. I don't care if this is your true value, whatever that is, or if this is how much you can put on the table. That's what I maximize. But it's a bit of a difficult argument with economists, let me put it that way, right? So what actually are you maximizing here, right? So it's kind of these kinds of things that you get into. And what statements can you actually make, right? Good. How am I doing in time? I'm slowly getting to an end. Right, so I think this is pretty much the end of the story. First point that I wanted to drive home, a large part of economic theory really focuses on the good cases in my classification. So those are the ones that are convex. And this is a really nice story to tell if you think about it, right? So, oh, we have these markets. We don't need to go back to pre-90s where there is the central decision maker and he is the dictator in this economy and he tells everyone, every generator what to do and so on. We have a market and everybody, we get an efficient solution because they just reveal what their costs are and how much they value electricity. And the market will solve it. There is this invisible hand, right? And that's the economist's argument for a long time. And in many cases, it's actually a strong argument, right? So I think the bottom line of what I want to tell you is, but you have to be very careful what assumptions you make, right? So when we have non-convexities, things can go pretty wrong. I think what the good news of maybe today's class was, sometimes these approximations are kind of reasonable, right? From a more engineering perspective, that might be good enough, kind of. But still, there is a lot of engineering detail on how you really cast it. I was telling you about these differences between what the US Americans do and what the Europeans do and how they clear it. So there are trade-offs, and you want to make these trade-offs in a principled way. But it works decently well, I would say. But details matter. Right, so maybe it's not so bad, that's what I'm telling you. But what I was also telling you is if you include a seemingly innocent additional assumption, so maybe you care about are there some caps on what a particular buyer is willing to pay, and you want to take that into account, then you actually end up with fundamental problems where there is no easy solution. So for these types of bi-level integer programs, there are not even approximation algorithms that would help you, right? So at least not that I know of yet. So I think for maybe very specific ones, but in general, while we have a lot of literature on approximation algorithms for standard NP-hard problems, you're pretty much alone if you go to that level of the polynomial hierarchy. Well, and that's pretty much it. So I think that the main punchline is if you do market design, and I think that should be a home run in this community, then computation matters, right? So it's not only efficiency, incentive compatibility, computation is really important, and you have to be very careful which assumptions you make, and whether based on these assumptions a market is indeed the right solution for resource allocation or it is not. And with that, I'm happy to answer additional questions that you might have. At the sim round, yeah.
Going back to the slide before, is it possible for the third builder to misreport, or like do they have could it have any other incentive to misreport if it doesn't know the budgets of other participants?
No, this is kind of okay. So this result doesn't hold anymore if budgets are public. Yeah. So if you're interested in that, I'll be happy to point you to the paper. It's on Archive. So that's a subtle difference. If public budgets are public, then there are ways to make this incentive compatible, right? This is just if you don't know both kind of budgets and values. Good question. Yeah.
Could you re-explain for dummies the very last slide, 47, why if you look at the cap value and not at the bidding value plus the per budget constraint, you destroy the website?
So remember again the objective function if we do welfare maximization of that sort, how I defined it, so aggregate surplus, so or gains from trade. This is all the same kind of, right? Then there are no budgets in a way, right? So we just look at the values, right? And what we do here is we compute an outcome if we only take the capped values into account, right? And I mean, you can make this arbitrarily bad. So it's kind of a truncated valuation of yours that we take into account. And that truncation might be such that, and here we didn't manipulate it in a particularly bad way. We just, truncate, so you're saying your actual net present value for the goods is, I don't know, 100,000, and maybe we truncate it at 50,000 or whatever. Quite obviously, then, if some of the values are truncated, we might make, we determine an allocation or a dispatch that, from a welfare perspective, might be the wrong one, right? So the good question now is, well, okay, what should you take into account? Is it really the capped values only, right? So you could make an argument for that. I think the attention, I just wanted to draw your attention to that because it's not so obvious. Then you get into a whole lot of judgment that you have to make all of a sudden, right? So is that any reasonable, this budget cap? So where does it even come from, right? And so if you're interested in that, there is an interesting game theoretical or contract theoretic aspect to this if you make the game larger in the sense, so somebody sets the budget, right? So where does the budget come from, right? So one argument among economists is often, why do you care about budget constraints? We have an efficient financial market, so there are no budget constraints. If you're in need, you just go to the next bank, make a compelling case, and you get the money that you need. That's maybe not always how it works, and in particular, you can. There are models where you kind of model the entity that is participating in the markets, and often you have principal agent or delegation problems within a company, right? So say there is a bidding team and there is a CFO, and they are not necessarily incentive aligned, right? And you have some hidden information. So the bidding team wants to win a particular package, and they know the real value, but the CFO does not. So in order to discipline the agent, he kind of puts a budget on top of it. So you can make this a larger game where you also try to understand what happens if we understand the strategic issue within the company, and the company is not just one payoff maximizing entity, right? So, and then auctions need not necessarily to be efficient, right? So it's all modeling exercises, and I'm not saying that everything, all these models are necessarily super real world relevant for electricity markets right now, but I think the only thing I wanted to achieve is there are a couple of assumptions that you really want to be careful about, right? And kind of the budget constraint is something that just makes things really difficult, right? If you want to do it right. So I hope that was clear. So what we do here is really just solve it as solve the combinatorial exchange as if the budgets were the values, right? Versus, no, we do the real thing. We solve the bi-level integer program that takes into account both value and budget, and that's the efficiency loss that you get if you compare those two. Okay.
let's thank Martin again for a fantastic talk. Thank you so much.